Hello everyone. Uh, Here I am going to present to you a series of lectures about how to analyze the data from a neutron detector array, such as the one at NAND, which is the National Array of Neutron Detectors at IUAC, New Delhi. The purpose of these experiments is to determine the pre-fission neutrons and associated data, such as mass and angular correlations. Here in this first lecture, I am going to talk about how to calculate the angles theta NF1 and theta NF2, that is the angle between the neutron detector and the fission fragment. And this part is crucial in the next part of the analysis, which requires you to do the analysis of neutron spectra using root, and then eventually you have to do the moving source fits where these angles will be required. Let's get started. First of all, I want to make you aware of the website. So this lesson will have associated files which you will need, and you will find these files available on the website. So my website is ambarchatterjee.com, and here in this website also you will find a link to my root videos. So if you are familiar with root already, that's good. Otherwise, please also read and understand my root videos, which you will find linked over here in the website. Once you are in the website, you can click in neutron array, and in the neutron array part of this website, you will go to a page which I have shown you on the towards the right. That is here, and this video which is going on now can be started by clicking this button here, which is marked as click. The files which you need, the support files for this lesson, it's called NAND lesson 1. You will find it under NAND01.targz. So this TGZ is a tar zip file, and it can be opened by an archive manager, or simply right click and extract here into a folder. There you will find all the files you need to work on this lesson. So let's see what this lesson is about. First of all, I think all of you probably know, since you're reading this video or watching this video, probably you know that at IUAC New Delhi, there is an array which is called the National Array of Neutron Detectors, and it is a large spherical assembly in which there are approximately 100 neutron liquid scintillator detectors. These detectors are arranged in 8 rings. Each ring is actually a horizontal plane, and these the angles at which the detectors are there, the angles they make with respect to the beam direction, they range from 9 degrees to 350 degrees. The number of positions where the liquid scintillators can be arranged are actually 111. In the mechanical assembly, there are 111 positions. In actual practice, we have been using approximately 100 liquid scintillators, and in some experiments you could be using a smaller number. But either way, we label the positions of the detectors. The detector label is very important. You have to watch. So when you see the detector label, you also know which detector position it is at. This is the important part. So later on we'll be dealing with the detector labels, and this will determine the geometrical position where the detector is placed. The time of flight path, namely the distance of the neutron detector from the target center, is 175 centimeters. At the center of this assembly, there is a spherical scattering chamber. Inside this spherical scattering chamber, we will be keeping two multi-wire proportional counters. The main one, which you see here in the diagram towards the right of the target. So at the center, you can see the target ladder. This scattering chamber is again externally controlled with the help of control motors, and these motors can reposition the target height. It can change the rotation or the angle at which the target is placed with respect to the beam, and it can also move the angle of the two turntables here on which we mount the multi-wire proportional counters. So these multi-wire proportional counters are large in area and they are used for detecting the fission fragments. They are position sensitive multi-wire proportional counters. We determine the position at which the fragment 1 has been detected. The second MWPC, which will be located at a backward angle, will be used to catch the complementary fragment, and this is useful when we try to distinguish between other events which are not fission. So our main interest is in fission gated neutron spectra. So we must have the detection of fission done properly, and that's why we detect both the fragments. Although in principle we could have detected just one fragment, and we know the position of the second fragment because of the kinematics which gives you the folding angle, but still we get a better chance of rejecting other beam-like particles which come at forward angles if we use two multi-wire proportional counters. So this is why two multi-wire proportional counters are in use. But important is that these are large area, so the multi-wire proportional counter is not small. So when you detect the fission fragment, you can't get the angle. You can't ignore the fact that it's a large area position sensitive detector, and the angle precise place where the fission fragment has been detected inside this detector is very important to determine the precise angle at which the fission fragment came. And it is not correct to try to deal with the entire MWPC1. I'm talking about now the first MWPC in which we detect the fragment. The secondary MWPC is only for getting purpose to ensure that we detect fission. So we won't be talking about that anymore. So as I am writing here in this slide, we need to divide the MWPC into sections. Some people feel that one doesn't need to divide the MWPC into sections and they make only one big section in the middle. I have shown that in the diagram on the left, which I have called as bad analysis. So a bad analysis consists of taking the entire MWPC as only one big slice in the middle, one large central area, and do the analysis only with that. Now this is bad. I will not only say bad, but it is very bad, because if you do that, you are restricting, you think that you are trying to restrict to one particular angle, set of angles, which is a small cone, and with that you will get away with the analysis in a simplified manner, which is not true. If the section which you choose in the middle is large, then the angles theta nf1 and theta nf2, this will change over different points within the section, leading to large errors in the moving source fit analysis. So not only the fits will be bad, the physics extracted will be highly questionable, and it's not recommended that you do the analysis like this, although I have seen many students and even published papers have done it this way, but it's entirely wrong. So not only that, if you make the section smaller, which is what you would be tempted to do, because when I say the angles are changing, so you say, okay, in that case, let's try to make the section small. But if you make it small, then what you are doing is you are throwing away part of the data. So this data is actually very valuable. You have obtained this data after getting beam time in a national facility, and it's not everyone who gets this opportunity. Having got that data, it is our duty to faithfully do the analysis without throwing away any valuable data. we will get better results. And so I have given you two choices here, the two diagrams on the right. I have called it good analysis with 6 sections, and if you are ready to do a little bit more work, you can do still better with 12 sections. So how many sections are necessary? This we will take a decision towards the end of my presentation today, but also later on when we try to do the analysis, we'll try to find out whether 12 sections is better than 6, and this you can decide. But at a very minimum, I advise you to have at least 6 sections. Now, the reason why some of the students are staying away from making these sections is that when they see the amount of work which is involved, they get into a fear psychosis. They feel that they have to do a lot of analysis. It won't be possible to complete it. It may take months or years, and they think that we must simplify the problem, and they start the analysis with a smaller number of sections and sometimes even a smaller number of detectors. As we will see today, that once you organize yourself, so you know what happens is that you have the data. Once you have the data, you must think about what you are supposed to do and plan it out. Once the planning has been completed, and this I am helping you to do through my series of videos, and I assure you that the entire analysis with 600 spectra or 1200 spectra will not take more than a few days of work. And then you come to the moving source analysis, and again, if you write the program carefully, I call it a structured programming. So if you do the program, I am going to present to you here in this series of videos all the programs that you will need, including the root programs which you have to write, and I will show you how these programs can be written in a structured manner. If you follow my video, I assure you, whether you want 600 spectra or 1200 spectra or more, it's not going to take any additional time compared to doing it for just one detector or one MWPC section. It's going to be the same because your program is structured and it can handle, and nowadays the capacity of computers is very fast. So getting 100 spectra takes approximately the same amount of time or work as just one spectrum. So don't fear, go ahead and make at least 600 neutron spectra from the root analysis. That is if you have 100 neutron detectors. If you have a smaller number of neutron detectors, well, for that smaller number, but at least 6 slices, minimum 6 slices, if not 12. Now, why a person who's doing the analysis gets puzzled with this, and why even they have published the papers even from IUAC after having completed the experiment, they have done the calculation of angles by hand. That means they haven't realized that you can't do this way. It's error prone. Even the published papers have got mistakes in the angles. The angles are incorrect. The analysis has been done probably with incorrect angles. We don't know, and therefore the physics extracted can be doubted. So while you are planning the experiment, please make sure that you plan it well. After the experiment, the analysis has to be done in a very planned manner. Clearly, for calculation of angle, a program is required. If you try to visualize the three-dimensional neutron detector array in your mind and try to think that my neutron detector is like this, up here, left so much, and then my fission is going here, and then what is the angle? If you try to this, you will go nowhere. It won't be possible. But you see, you can easily formulate this problem in terms of three-dimensional vector geometry, and then no visualization is required. You just, it's purely algebra. You write down the angles, you write down the vectors, unit vectors in the directions required, take the dot product, and then you find out the cosine of the angle, which is, it's as simple as that. So a small program will be written. You will find that the real part of the program is only about 30 lines long. You just run that program. It runs instantly. It gives you all the answers, and then you use it in the moving source analysis. So it doesn't take any extra time. So please go ahead and try to understand what we are doing here. And the other reason why people sometimes dissuade the student from making calculation for large number of neutron spectra is that they feel that the statistics will be less. That means you have got a certain amount of time for which you have collected each run, and the number of files in the run which you will chain up together, and then you will analyze it in root. They feel that the statistics will get distributed over so many slices. Once we divide the the fission detector into slices, once we make six slices, then the data is divided into six parts. So the statistics of each spectrum will be reduced. They feel that if you make only one spectrum, the statistics will be six times more. Now this is wrong again, completely wrong, because we do not analyze the neutron spectra individually. The analysis is done simultaneously of all the spectra. So no matter how much division you have done, the statistics is actually the total statistics of all the data which you have collected. You are not a single byte of data literally is left out. You are doing the complete analysis, and that is what is required. And if you try to take a small area in the middle of the detector, you have left out more than 50% of the data. So that is what is wrong. You must not do that. You must analyze the data completely, not leaving out any data, and you must have the angles correctly. And the only way of doing it is to divide the MWPC into slices. So here is the work which is required. I have done everything for you, so the amount of work to be done from your side is very little. The programs are provided here in my presentation. I am demonstrating how to run it. So you just have to run the program and for your geometry, and within a few minutes you have all the angles that you need. So here is the first thing which you have to do. You have to realize that you need a coordinate system. The coordinate system which we are going to use will have the z-axis along the beam direction. Now this is probably what you already know, all of you in nuclear physics. Whenever we do any work, we know that we take the z direction along the beam axis. But the x and y, this is also important. So we are going to stick with only one frame of reference in which the origin is at the target center. The z-axis is in the direction where the beam goes. So in this picture you can see that the beam is going from left bottom of this photograph here towards the right side. Towards upwards, and that is z. So I have labeled that as the z-axis. That is the direction in which the beam is traveling. The y direction is going to be upward. That means from floor towards the ceiling. That is the direction. So if you are standing in front of the detector looking at it, then if you raise your arm upwards, that will be the y direction. And if you, from the perspective of this photograph, the x-axis is on the left side. So if you stand in front of the this neutron array and you look towards where the beam is going, then the x-axis is to your left and the y-axis is upward and the z-axis is in the beam direction. Now, when the NAND detectors were constructed, the frame for this NAND geometry was constructed. There's an engineering diagram available for this, and this file, which is called NAND detectors spherical.pdf, was constructed. This file is available from the NAND group in IUAC. You don't have to worry about getting this file because I have provided this file for you. It's there in when you get the this star zip file. Inside that, one of the files is this NAND detector spherical.pdfs. So you don't have to hunt anywhere. This is what this file looks like. I'm explaining it to you. There are actually, I think, about 4 pages of this file, so I'm not showing all the 4 pages. You can open the file and have a look. But this is what the file looks like. It gives in each, so there are several rings I mentioned. So here, for example, ring 1, then ring 2, then ring 3. So in the first 3 columns, the Cartesian coordinates, that is the x, y, z, in that frame of reference which I already explained to you in the previous slide, the x, y, z, in that frame of reference, the values of x, y, and z are given for the neutron detector location. and then it's converted into spherical polar coordinate system, that is r theta phi, and those angles are given, those dimensions are given in the next three columns under spherical coordinates r theta phi. The R is going to be 1750. All the detectors are at exact same distance from the center of the target. So R later on is R is not listed. That column is left blank. That is because the number is 1750. Just repeat it here. And finally, in the last column is the detector marking. Now you know a little bit about the detector marking, because when you are working with this neutron detector in the root file, the labels of the signals coming out from this detector, they have got this label. So for example, the PSD output, that will be shown as P100 or P218 or P2306. That these are the detector labels, and the corresponding signal in the root file, they have also got this label. So once you know which detector you are talking about, the label, you also know from this file 9 detector spherical.pdf, from this file you know its xyz coordinates, you also know its r theta phi coordinates. So we are going to work with the r theta phi only, and we are not going to work with the xyz, we don't need it. We need the detector label, and we need the theta and phi. R also we don't really need, because it's the same fixed value 1750. So the first thing which we are going to do is that we are going to make a new file, and in that file we will and also we don't want to work with a PDF file, because our program has to read it. So our program will be able to read a file provided it is a text file. So we are going to make another file, and in that file there will be just the detector marking, or I call it as label, which is the last column here. I move it into the first column, and then I list the theta and phi. We are going to do this for all the 111 detector positions, although in every position the detector is not there. Some positions there is no detector over there, and in your experiment perhaps you would be not using all the detectors. You might have a situation where you are using a lesser number of detectors, but nevertheless in this file we are going to make a complete file with all the 111 detector positions. And when we do that, we'll get a new file, and that file will be important. This file again I have provided to you. So now I, for a minute, come out of this PowerPoint presentation and show you the files. So you extract the files. When you extract the files, so I'm going to minimize this PowerPoint presentation and let me show you. So when you go to the website and then you locate this file and nand01.tgz, and you download it, make a folder, place this file in it, and then right click it, and then you say extract here. This is the important thing. So you download this file, put it into a folder, right click it, and then you say extract here. When you do that, then you will find that you get this file which I was talking about, 9 detectors spherical.pdf. See, I open it for you. This is your PDF file. It has got several pages, and this contains the full angle information up to 8 rings. Yeah. So this is 9 detector spherical.pdf, but you have to convert it into a text file, which our programs can. I have done that for you, and you can check it. I just hope that I didn't make any mistakes. So I request you as students to compare this file with this and take a look, see that there is no mistake. So this is the file, which is a text file now, and I have put the detector label. I put an E in front of it because I just wanted to make it a little bit more clear that this is not a number but a label. So I put E in front. There will be also a different outputs, so this E will be there, then P will be there, P, and then T will be for the time. So these signals will be there from in your root file. But anyhow, this 100, for example, this is a label, 218, this is a label, and this is your theta, and this is the phi of that detector. So just 3 columns, and the number of lines in the file is 111, because we have 111 possible detector positions in the frame which supports this structure, As I said, in your experiment, not all detectors will be there, so those parameters will not be there in your root file, or if they are there, they are not being used. It could be like that. But it doesn't matter. Let this file be complete. Let it have only all the 111 positions. And then when we use this file, or rather another file which we will derive from this, it will have also 111 possibilities, lines, but we will use only those lines from it which are relevant for the experiment. So that was about this land detectors.txt file. Now let's go back to my PowerPoint presentation. And in the PowerPoint presentation, we will have to look at the programming which we have to do, the formulation which we do to calculate the angles, as well as the writing the program. So I'm explaining that to you, and here it is. So I'm going to look at the XZ plane view of the MWPC1. The MWPC1 is placed at a forward angle, something like 40-45 degrees. That's the usual angle at which you place MWPC1, and it is used to detect the first fragment. That is the one which I have shown here. This XZ plane, what is it? So XZ plane is the horizontal plane. Okay, you see it here. So I'm in the horizontal plane. Now my MWPC1 is become vertical rectangle facing towards the target. The distance from the target position to the center of the MWPC, that I'm going to use the symbol D. So this distance D is the distance of the MWPC to the target. And the angle which this central point makes with respect to the beam axis Z, I'm going to call it as theta MWPC. Now these distances and this angle will be known to you, because when you are doing the experiment, the first thing you do is you set up this MWPC and you record this angle, theta MWPC, and you also record the distance. This is part of the geometry, you have to measure it, and in your logbook it's there. You also know the size of the MWPC, because the MWPC is not always the same MWPC. There are several MWPCs available in IUAC lab, and that one which is at that moment working the best, it is decided to use two of them will be used. One at so I'm working with MWPC1, and in this particular experiment in which I participated, the size of the MWPC was 125 millimeters. So I consider it as minus 62.5 going up to plus 62.5, and I use the symbol lambda to denote the direction along the width of the MWPC from left to right. And if it's on the leftmost position, it will be minus 62.5. If it's in the center, that I consider as 0, and if it is on the right extreme, that will be 62.5. So this is the view of, or the plan you can say, of the of this MWPC plane, looking as though you are looking down into the scattering chamber from above. That's the kind of view that you have. And for the, now here you can't see the verticals because this is a picture taken from above. The vertical direction, I call it as Y, and I'm going to use the symbol YMWPC. So YMWPC is the vertical position where the fission fragment F1, where it strikes this MWPC. If it is 0, it means it has struck in the center. If it's positive, it means it's gone slightly up, and if it's negative, it means it's gone down. So, but this Y is actually the same as your Y in our lab frame. So in the lab frame, Y was vertical. So MWPC vertical is also, even though the MWPC is tilted with respect to the XZ direction, but in the Y it's the same. So YMWPC is actually the same as Y. In the experiment, you know that this the values of lambda and YMWPC, you will be deriving it from the signals from inside the root file. So you've done the experiment, you got the root file, and from there you will be extracting these quantities lambda and YMWPC by taking the difference of the signals MWPC1 x right minus the one x left, and you'll have to multiply it by a certain calibration factor to convert it into millimeters, and you do the same way for the y direction also. That will be event by event. Now, what we are going to do in the route analysis is that we are going to place position gates and build coincidence neutron spectra. So each of the neutron detectors will be having a coincidence with fission, and the fission which we are talking about will be corresponding to these six spots if you have made six sections, or it could be 12 spots if you have made 12 sections. And so you have to then make build these. This we will do in the route analysis later on. I will show you how we are going to write the structured route program. So people also fear here that the route analysis having 600 spectra will require 600 sections where with many lines. So the route analysis program will consist of something like 6 into 10, say 6 yeah, 600 into 10, so 6,000 lines. They think that the root analysis program will require minimum 6,000 lines. They are mistaken, because when you write a program which is structured, then there are loops, and then the program is extremely compact. But looking at the root programs which the students are sending me, I find that they have not structured their programs. They are writing the program line by line, and if you have experience in coding, you don't code that way. What you do is you have to code as a structured program, so that when you move from 6 sections to 12 sections, or if you want to try one section also, the program is the same. You just have to run the program in a different manner. That is called a structured program. So we will be writing a program which is extremely short, and it will be able to do the route analysis. This we will do in the next lesson, but today's lesson is only about the angles. So I am showing here the MWPC divided into 6 sections. The central point of each of the 6 sections I have marked here with a red dot. And now we are going to work out the angle theta NF1 based upon the lambda and the YMWPC value at the center of each of these 6 sections. And for theta F2, we will take the angle because considering the folding angle. So if F1 has gone in the direction of the red spot, at what angle would the F2 have gone is known because of the folding angle. The folding angle can be calculated from kinematics, fission kinematics, which you can do. And so for your reaction, the folding angle is known. We do not calculate the theta NF2 based upon the actual position in MWPC2. This we do not do because that will be event by event, whereas we are going to build spectra, and we are going to have spectra based upon MWPC1 with position gates. So we will be, to get these slices, we will be putting on the lambda and on the YMWPC, which we extract in the route analysis. We will be putting rectangular gates which will correspond to these 6 sections of the MWPC, and then we will be generating for each of the 100 neutron detectors, or 111 maximum neutron detectors, or whatever smaller number you have in the experiment corresponding to that, 6 times that, one for every slice. And in each coincidence spectrum we will be having theta NF1 as well as theta NF2. So how do we go about calculating these angles? So it's rather easy, because you are not supposed to do any visualization. You simply make a little bit of 3-dimensional vector geometry. So look here now. So I have shown the same diagram again, and I have shown you that it's actually a tilted frame, x bar, y x bar, and z bar as compared to xz. If you consider that as a tilted frame in which the MWPC is placed, then you all know how to do a tilted frame, 2-dimensional tilted frame, and that works out in terms of the familiar cos theta sin theta. This is actually, you can say, class 12 maths, or vector geometry, or maybe first year BSc, something like that. It's just a very simple exercise, but you must do it properly and then formulate it as I am showing you here, and then write the program based upon the formulation. This is what is required, and then once you have done it, it's easier than doing it manually, and it doesn't have any chance of making any mistake. So I have written the programs for you. I have debugged them and the programs completely, and you can just use it. And if you are interested, you should try to write the programs on your own instead of taking the programs which I am supplying. You can work on the program yourself to understand more, but this is up to you depending on how much time you have. The entire formulation I have provided here, the codes I have given you. So here it goes. We first make the transformation from the lambda and d in this lambda and y in here, and this will be the three equations converting x, y, z, getting x, y, z from lambda. And the distance d, this is known to you because you have done the experiment, so you know the geometry. So you have to provide the distance d at which you have placed the MWPC, and also the angle theta MWPC. This depends upon your experiment. So based upon this, we are able to make this transformation into x f1, y f1, z f1. Now after doing this transformation, it's not going to be a unit vector. We are going to take a dot product and we are wanting to work with the unit vector. So let's first make a unit vector out of this. So whatever you get results xf1, yf1, z1, you just divide it by this normalization factor, which is the square root of the sum of the squares of the individual x, y, and z values. And then you replace the xf1, yf1, and zf1 by the normalized values. This is my equation 1. So at this stage, we got the f1 unit vector. We now have a unit vector which is pointing in the direction of the first fragment in the x, y, z coordinate system. Now when we are at this stage, we don't really need equation number 2 immediately, but we'll require it later on. So I want to know the polar angles also, or in the spherical polar system, I would like to know what are the coordinates of this unit vector. So that's r theta phi. R is 1, it's a unit vector. And what are the values of theta f1 and phi f1? Well, you know these equations. The cos z is equal to r cos theta, we say. R is 1, so cos theta will be z. So this is the equation. Theta f1 is equal to the inverse cosine of the z, and the phi angle will be the inverse tangent of y divided by x. Familiar equations for conversion of rectangular to spherical polar. Now, well, I guess you know that this tan inverse function, when we work it out in the computer, it can give negative values. Its range of operation is between minus pi by 2 to plus pi by 2. But really we want to work in an angle which is positive, 0 to 360. The same applies, by the way, I forgot to mention in that file 9 detector spherical.pdf, you will find mention of negative angles. So there the negative angles you should be adding 360. So I work with that. So when I make the another file, the text file, there I have added already 360 and made sure that all the angles are positive. So I do that here in the program also. If when you make this calculation of theta f1, if it turns out to be negative, then we just add 360 and get a positive. This makes it easier. Of course, later on, the trigonometric functions will still work, but it's better to work with the positive angles because that's what it should be. Okay, that was about equation 2, but what we really need now is the equation 3, which is the spherical polar angles of the neutron detector theta and phi, and these are already there in the file. Okay, so I think I should show you, yeah, I showed you already the file which we, that was this file, neutron detect, neutron, not the spherical, but the NAND detectors.txt, this file which is there in your download. This has got theta and phi of the neutron detector, these numbers. So we will be reading in these numbers in our program, and we will be able to utilize. Okay, so that's the equation 3, theta neutron and phi neutron, converting it into rectangular, and then the angle between the unit vectors of equation 1 and 3, and you take a dot product and then you take the inverse cosine, this will give you the angle. So we are interested in this theta NF1. It will be given by the inverse cosine of this kind of expression which I have given here. This is what we are going to code. So you have the unit vector here, equation number 1 for the fission, and from here with I have taken r equal to 1 and x, y, z based upon the angle. I want a unit vector, so I make a unit vector along the neutron direction, that is equation 3. Then I take a dot product of 1 and 3. I take the and get the angle by taking the inverse cosine. So this gives me theta NF1. We also need theta NF2. So first of all, having got the angles of theta F1 and phi F1, that is the fission 1, which we got here, equation number 2, we got it here. This is why we did it here, although we didn't need it immediately, but now we need it. So having got that, now you calculate. So this is the diagram again. Now the fission 1 has gone like this. I've shown it F1. So where will the fission 2 go? The fission 2 will go in the angle which is at the folding angle, but it will not be in this XZ plane. See, F1 I have shown here, but it won't be in this plane. F1 could be upward, downward, and still detected, because the MWPC, I have shown you only a top view of it. It is extended in the y direction, that is the direction perpendicular to the screen, and so F1 could be going up or down, and accordingly F2 will be going down or up, opposite of that, and at the same time the tilt angle will be equal to the folding angle. So once we know the folding angle, then this is the calculation. The theta of F2 will be the folding angle minus the theta F1. And the phi of F2 will be either theta F1 plus 180 degrees, or it could be minus 180 degrees, depending upon whether F1 was less than 180 or greater than 180. So with this help of this calculation, you can determine the theta and phi spherical polar angles of F2. And then now you can, equation 4 helps you to get again the unit vector, the x, y, and z of the unit vector for F2, and then once again you take a dot product with the neutron unit vector and take the inverse cosine, and you have got the answer for the angle for the between the neutron detector and the fission fragment number 2. So this is what we do. We have to code these, and the first, I'm going to show you two programs. The first program is a GUI based program. It uses a graphics library GTK4, and here you have to enter the angles into the boxes which are provided, and then press run, or calculate, rather you press calculate, and then it gives you results. But this will be, just one result at a time. As I explained, there are going to be something like 600 or more, maybe 1200 results which you have to calculate. So if you are going to use Theta Solver 4, by the way, Theta Solver 4 is an upgrade of Theta Solver. ThetaSolver.c I wrote 10 years back and provided it to students. I still have it, it still works, but now I have upgraded it to the library, graphics library GTK4. In those days it used to be GTK2. So now I am in today's lecture I am providing for you Theta Solver 4. Please use that. And just after explaining Theta Solver 4, I will show you that you don't really need Theta Solver 4 as much as you need the second program, which I have called as Theta Calc, because that will give you the required text files rather than making the calculations one by one. So Theta Solver 4 is for you to get used to the system and do some little bit of work with that, just to verify things and get a feeling for the angles. But later on you can just use the Theta Calc program, which is not graphical. So here I am going to tell you now how you can install and run Theta Solver 4. I am assuming that you are working in Ubuntu Linux, although you could work in any other Linux system too. but here I'm explaining. If you have any other Linux system where you want to run and you are not able to run it by the commands which are here, just let me know. I will help you out. So as usual, get in touch with me by email. My email address was given to you on the first slide of this presentation. So go ahead. But anyway, if you are having Ubuntu Linux, then you must first install the graphical library which is called libgtk4dev. And the command to do that is sudo is the super user do command, and apt is the installer. And so apt and then install, and this one. If you have already installed the GTK4 graphics library previously, as is true for me, then you don't have to do it again. And if you do it a second time, no problem, it will just show you that it's already installed. So after having done that, then you need to compile theta solver 4. So theta solver 4.c, this file theta solver 4.c is already available to you because you have downloaded it, and then you compile it using the command which I have illustrated here. This command is rather long, but you can cut paste it from inside the file itself. I'll show you how. And then when you want to run it, then you put dot slash and theta solver 4. So these are the steps for now. I will take a pause from this presentation part and actually go to the running this program for you, so that you can also do the same later on. So I am minimizing my presentation window, and this file I have already shown you. So you see, when you have done the unpacking, you will have got this file theta solver 4.c. You can open it in the editor. This is how it looks like in the editor view. So basically there is one section of it, function. It's a function called calculate. Okay, and it starts at line 10 and it ends at line 50. So there are only 40 lines, of which many of the lines are actually blank, like here, and many of them are simply comments. So you can see it's a very short program, right? There's nothing much in it. I mean, if you wanted to write the program, you could perhaps have written it yourself in a few minutes. But even that I have done for you, and the algebra of it I have explained in the PowerPoint. So, and the notation is fairly straightforward. So I use underscores whenever the subscript appears. For example, theta MWPC. So what is theta MWPC? You know, it is theta underscore MWPC. It is the angle of the center of the MWPC with respect to the beam direction. D is the distance of the center of the MWPC from the target. Theta fold is the folding angle. This is determined from fission kinematics. You have to supply it. The program doesn't know what is the value of the folding angle. It depends on the reaction, and you have to calculate it from fission kinematics and supply this value. Then comes the now later on in the second program you will not have to supply theta, and it will take for all the detectors. But here this is a manual first program. Here you have to decide what is the direction in which the neutron detector is sitting. That is called theta n and phi n. So you take one of the neutron detectors and supply to this program the angles theta and phi. You need to also supply lambda. Lambda is the distance of the place where the fission fragment has struck the MWPC1. Center is at 0. On the left of it is minus in millimeters. So this is lambda, and this is the height inside the MWPC, again in millimeters, where the fission fragment has stuck. Once you supply these quantities, the first part here, this entire line, are inputs. These numbers you have to supply. Once having supplied that, in the next line here, this is calculation. So the program will make the calculation, and it will get at the values of theta f1, the phi of f1, and the theta of f2 as well as the phi of f2. So the first four quantities f theta phi are of the two fragments, the direction of the two fragments, and it will calculate also for you the main quantities of interest are the theta nf1 and theta nf2. These are the angle between the neutron and the fission fragment. This is the two key variables which we wanted to derive. So how do you do that? Well, the equations I already explained, so you will not have any problem in reading this. It is exactly as per my PowerPoint presentation. The PowerPoint presentation file itself, apart from the video which you're already watching, you have, when you download, you will get the PowerPoint itself. So you can refer to the PowerPoint. All the equations are given there, and you can correlate it with this calculation. You can also rewrite this on your own. You can also do the algebra in some little bit different way according to whatever you have. For example, you could make the dot product in polar coordinates instead of working with rectangular coordinates. So I have done conversion from spherical polar to rectangular and then taken the dot product. We could also do it directly, the dot product in spherical polar coordinate system, for example. You can rewrite it that way. So it's up to you. But I have given you the program here which I have written, and it's straightforward. You need not read the rest of it because that is the GUI part which I am not going to explain. You don't have to read all this part. And later on in the second program, and the second program will be your real workhorse. This one is just for demonstration. So the second program will use this exact same subroutine calculate. So just understand only this part, and that should work for you. All right, so let me go back to my presentation. So you understood about theta solver 4. Yes, how do you run it? So you know this, all of you can manage this out. So you were looking at this, the compilation command is available inside the program. So let's start by installing the graphics library. What you do is you go to your folder here, and then you say open in terminal. So right click and then open in terminal. So now we have got a terminal window. I'll make it a bit bigger for you. And then here firstly we are going to install. So let's look at the command here. That was here. So it was this command for installing the graphical library. So I just use the middle mouse button now to paste this here. This is the command. Now for me it's already installed, so I'll just do it for you anyway, but for you, you will have to install it. You now have to enter the password. Right, so it says that libgtk4 dev is already installed. For you, an installation will actually take place here if not already installed. Okay, that now we must compile it. So this is my compilation command. So I copy it here. Yeah, okay. Anyway, with the middle mouse button, I can do it. This is my compilation command. So now I compile it. So compilation got over and my executable got created here. To run it, instead of double clicking it there, it's better that we can see its output also. So we better run it from here, theta solver 4 / theta solver 4, and now it's running. Okay, so this is how it runs. Now you have to enter the numbers here. You see, this one is the theta MWPC, this is the distance D, this is the folding angle, and then we put the neutron detector theta and phi over here. We provide lambda and we provide y. These are all inputs, and then after that we press calculate, and then the results will come in these boxes. Okay, so you can also just directly click, for example, example 1, then it gives you certain one particular case, or example 2 gives another example, example 3. So these are for demonstration purposes. To actually run it for an interesting case for your own work, you need to actually well, I have given it here in my presentation. So let's do that. Okay, where were we? Yeah, here. So now after this slide, yeah, so this is your theta solver screen. You've seen this. You have to enter the values and then click calculate. Let's do that for one example. So I have taken an example where the MWPC size is 125 by 75, and then I made a table here. This table later on you won't really need it because my second program will actually generate this all the numbers which are in this table on its own. But anyway, I have given it here for reference, and I have given one example here. In this example, I have considered as though the fission has hit here in this 2. So the fission fragment has come in 2, and then the lambda should be 0 and the y should be 18.75. And the reason why lambda is 0 is because from if you see horizontally, then if you see from left to right, then it is in the exact center. So lambda is 0. But in terms of height, well, it's slightly raised above the median plane, and so there's a positive number 18.75. So you run this example, and if you do that, I've taken the position slice 2, lambda is 0, and the y is 18.75, and I'm considering the particular detector 2306. This is in ring 2, and you can see from the file that its theta and phi are having the values given here. I type these values in, and I ask the program to calculate by clicking this button calculate, and it gives me the results. 45.13 is the detected fragment angle. The phi comes as 5.39. The second fragment is going at this angle. Theta and phi is given here, and what are the theta neutron angles for F2. There seems to be some mistake here. This should be, this first one is F1 87.60, and for fission 2 it is 88.75. So this is F1 and this is F2. There is no mistake. So this is that, and if you want to visualize, then you can do it here. I have given the visualization of this particular example. The neutron is going that way. See this dashed line, and F1 is going this way. I have shown it here, and the angle which the program has calculated 87.60, this is shown here. I have not complicated by showing F2 also, and then the angle you can do that on your own. But you can see that this 3D visualization you need not do. You just go with the program, it gives you the numbers. That's what we need. If you want to do this kind of 3D visualization, it's quite difficult, and you have to do it 600 times or 1200 times, so don't bother. Let's go to the main workhorse. There's going to be theta calc.c. So this whole job, instead of doing it 600 times using this program, this was for demo. So with this you can do it, but you have to run it 600 times or 1200 times. So rather than do that, let's make a program which is not graphical. It's text based, and that I'm going to call as theta calc.c. This is also provided, and it gives you the same calculation, but puts the output into a file. So that's it. I will now close this presentation because I need not come back to it. Well, maybe I should come back to it for illustrating the last point. So let me keep it going for now, minimize, and this one we can exit. So exit program is done. Let's try to compile and run theta calc.c. So theta calc.c, as promised, is having the same subroutine which is as in the previous program. The main program simply reads the NAND detectors.txt to get the for each neutron detector. It finds out the angle from the file. You don't have to provide the details of each detector now. It knows about the neutron detectors from the file. What you have to provide is only what is changing in your experiment, and that section is here. It asks, and then it does the division into slices on its own. It asks you whether you want 6 slices or 12 slices. It doesn't work for any other slice number other than 6 or 12. I guess you could make it work for the other cases too, but I've given an example of only for 6 and 12. And then for those slices, it does the work for you and puts all the result in those 600 lines, 666 lines actually. So this is how theta calc will work, and you won't need this theta solver 4 after you have understood theta calc.c. So theta calc.c is to be compiled. Now there's no graphics, so it's just a simple line. This is the compilation command. So let's go here and let's paste this line here and compile it. Now we compiled it. The theta calc came here. Again, you need not run it by double clicking it here. Better to run by putting the /theta calc. So I run it and it's asking some questions. So it is asking for the angle of the center. In my example, I will run the same example which I am running here, and in that so that example is this one. So I keep for reference this slide handy and I start entering the data. In this example, my center of the MWPC was at 45 degrees and the distance of the MWPC was 270 millimeters. So 270, and then the fission folding angle was for my particular reaction which I calculated from kinematics, and the answer is 160 degrees. The width of the MWPC was 125 millimeters and the height of the MWPC was 75. These numbers could be all different for your particular experiment. How many slices do I want to make? Well, for now let's take 6. I think you can also try 12 on your own. So let's go ahead with 6, and the program is finished. As usual, computers are fast, so all the results which I want are generated in an instance, in an instant, and the answers are available in the angle neutron fission angles.txt. Now this file is not provided to you. It gets generated when you run the calculation because it is specific to your experiment. I can't provide this file to you because that would be for my geometry. In your case, these numbers would be different. So this is what the file will look like. It will consist of the label of the detector in the first column. It will show you the neutron theta and phi, and then there will be 6 slices because I have considered 6 rather than 12 slices. So for each neutron detector there are 6 slices, and these are the positions of the angles, polar angles theta and phi, where the fragment has hit the slice, center of the slice. And lastly, in the 2 columns are the important quantities, the angles which will be important in the moving source fit, namely the angle between the neutron and the fission fragment 1 and 2. Now when you go through this one, you will realize that the situation is very important, why we did the slicing. Here we have 6 slices. Okay. Now if you didn't have a slice, then you would have worked with all the slices as same, and you would have probably taken 86 degrees as the angle for theta and f1, and 95 degrees you would have taken. You can see that it would be wrong by as much as 10 degrees. For example, 95 is 84 here for the 6th slice. So the center of the slice representing the full slice is what we are doing, provided you have sliced it. If you don't make 6 slices, the whole thing is 1 slice and the angles will go wrong, seriously wrong. But this is a favorable case, where the neutron detector is sitting vertically up at 90 degrees. So it is just perpendicular to the surface of the MWPC. But if you go to some other case where that is not so, then the variation will be still more than 10 degrees. So a mistake of such a large magnitude is very serious, and one should not make such a big mistake before we start the moving source fit. So I have illustrated that, and with that I will end today's part, that if you have 1 slice, 6 slices, or 12 slices, or should we have even more? These questions can be answered. I take one example. I take this label 4186, this particular detector, and in this case, look at the variation of angle across my 6 slices. The slice 1 had 113 degrees, and this one is 129. So you see that there is a difference of 16 degrees between the first slice and second slice. If you had made only 1 slice, they would have had 16 degrees variation. You can see it would have been pretty bad for the moving source fit if we don't slice. With 6 slices, the error in angle will be reduced to only 3 degrees. And if you want to reduce the error still further, you can even work with 12 slices. So that decision we will eventually take, and if you are a student who is prepared to do more work, you can do the complete analysis with 6 slices and also with 12 slices and find out the difference it makes. So thank you very much. I have finished with whatever I wanted to say today, and in the next lecture we'll go on to the root analysis and learn how to write structured programs using root. And then we will write the program and we'll run it for a particular case and see how we can get results. and then eventually we'll do the moving source fit. Again, the moving source fit